Alright guys, this is November 30th through December the 4th. Let me kind of explain to you how we're going to do this. We are going to be looking at section 2 of chapter 1 that starts on page 86. I'm going to kind of run through some of it. We'll talk about some of it. Some of it I'm going to let you read on your own. Just because this section is a longer section. And if I try to make a video and go through every single tiny thing, this is going to be a huge long video. And I know you don't want to sit and listen to me for that long. So, some of it you will be responsible for on your own. Alright, so page 86, we're looking at functions and their properties. In the last section, we talked about some different things about functions, solving equations, looking at some of the behaviors of functions. Today what we're going to do is we're going to talk about domain and range, and we're going to talk about continuity and just different things. So let's go ahead and get started with this. If you'll look at the box at the beginning of the chapter, a function from a set D to a set R is a rule that assigns to every element in D a unique element in R. The set D of all input values is the domain of the function, and the set R of all output values is the range of the function. Alright, so we'll kind of talk about domain and range here in just a little bit, but let's go ahead and start talking about what is a function. How do we know it's a function? That's what the next little section is going to be about. So we have what we call the function notation, and a lot of times you're going to see it written like this. And we read that as y is equal to f of x, or the value of f at x. Alright? In this case, this is our independent variable. In other words, it does not depend on anything. And then y would be our dependent variable, so y would depend on whatever x is. A function can also be viewed as mapping of the elements of the domain onto the elements of the range. We've talked about this before. We talked about how to identify a function. If you remember, when we were looking at functions before, we were looking at x and y values. And we said, if I put my x and y values as long as my x only had one value, so in other words, if I put 1 in, and I knew that 1 can only give me a value of 7 for y, and 2 could only give me a value of 8 for y, as long as my x only gave me one value for y, then it was a function. Alright? So for here, if I did this, if I said that if I put 1 in for x, and it could give me a 7 or it could give me an 8, then this is not a function. Alright? Because my x value could give me 2 y values. It's very simple. It's very similar to when we're talking about domain and range. You can look at domains as your x's. Alright, so domain would be your x's, and range would be your y's. So as long as your domain is only going to give you one range, then it would be a function. If your domain or your x gave you multiple, then you're going to not have a function. All right, and we're going to talk about another simpler way to determine functions here in just a moment. All right, like I said, some of this you need to read. If I skip through it, just kind of make sure you're reading the paragraph that I'm skipping through, because I'm just kind of hitting high points and low points here. All right, so defining a function. Does the formula y equal x squared define y as a function of x? All right, let's just look at the answer. It says yes. Y is a function of x. In fact, we can write the formula in function notation. F of x is equal to x squared. When a number x is submitted or substituted into the function, the square of x will be the output, and there is no ambiguity about what the square of x is. All right? You can also graph it. Now, graphing it is a lot simpler, identifying it as a function. And let's talk about why. All right, if you will look at example number 2, they've given us 3 graphs. All right, and they want to know which of the 3 graphs is not a function. Well, let's look at this. Remember I told you that if for each x value, it could only give me one y value. So I could literally sit there and go through my x values and see, am I only getting one value for y? If you look at this on the first graph, you will see that every x value only gives you one y value. On the second graph, same thing. But look at the third graph. The third graph, if I look at, let's say I look at -1. -1 would give me a y value of 2. It would also give me a y value of like 1/3. And it would also give me a y value of -2. So my x value of -1 actually produces 3 values for y. So therefore, this is not a function. Now, another way that we can do this without actually going through every single tiny x and y value is we can do what we call a line test. It's called the vertical line test. All right? And so what that means is I can take a vertical line. All right? And I'm going to show you how to do the vertical line test. I've got to clean off my paper here. And you can do this with any type of material. I've got an overlay that I'm going to use here. And let me show you what the vertical line test would look like. So it is a vertical line test, which means I need to draw a vertical line. All right, so here's my vertical line, and I probably shouldn't have drawn it that thick. We'll just draw a very small vertical line. And the way that you would do the vertical line test is you would take your vertical line and you would run it across your graph. And if at any point in time that vertical line touches your graph in more than one spot, then it is not a function. So I can run this vertical line all the way through graph 1 and it never touches in more than one spot. Same with graph 2. I'm going to run this vertical line down graph 2 and look, nothing. But when I look at graph 3, notice my vertical line touches the graph in 3 different spots here. So therefore it tells me that my x value would produce more than one y value. So that failed the vertical line test. Alright? And most of these you can eyeball. Like you can look at it and see. But you can do the vertical line test. And then Guys, it tells you the definition of vertical line test at the bottom. And it says that it is a function of x if and only if no vertical line intersects the graph in more than one point. That's the whole point of the vertical line test. Alright, so page 88, we're going to look at domain and range. We're going to talk about how to find the domain and the range. Alright, we're going to very quickly go through this. We will usually define functions algebraically given the rule explicitly in terms of the domain variable. The rule, however, does not tell the complete story without some consideration of what the domain actually is. Alright, so, unless you are dealing with a model like volume that necessitates a restricted domain, we will assume that the domain of the function defined by an algebraic expression is the same as the domain of the algebraic expression, the implied domain. For models, we will use a domain that fits the situation called the relevant domain. So let's talk about how do we find the domain of a function. Alright, so if I'm looking at example number 3, f of x is equal to the square root of x plus 3. Now remember, my domain deals with my x values. So in other words, what I want to know is, what can I not put in for x? I can put in a -3 and I would get the square root of 0. I can find the square root of 0. Alright? I can put in a 2 and I would get square root of 5. I can find the square root of 5. So what numbers would make this statement not true? Alright? So we've already said I can put -3 in there, and I basically can put -3 on up. Let's see what happens when I do -4. If I put -4 in here, I get the square root of -1. At this point in time, the square root of negative numbers is undefined. So therefore, I know that my domain has to start at -3 and go up. I cannot put anything smaller than -3 in this equation and it be a true statement. So my domain has to be, x has to be greater than or equal to -3. We would write this as an interval like this. -3 is included, so I'm going to use a bracket, and I would start at -3, and I would go to positive infinity. So this is what my domain would be for this function. Alright, looking at the next function, g of x is equal to the square root of x over x minus 5. At this point in time, I need to look at this and see, okay, can I put negative numbers in for x? Well, on the bottom, it wouldn't matter. I could put negative numbers in there. But if I put a negative number in for x at the top, would I get a true statement? I can't find yep, that's it. The square root of a negative number right now. So therefore, I cannot put any negative numbers in there. Now let's look and see what would happen if I have 0. If I put 0 in there, I get 0, the square root of 0 is 0, over -5. Can I do that? Yes, I can. So I know that I have to start at 0. But here's what else I need to know. What if I put a 5 in here? A positive 5. It wouldn't bother the top, but what happens here? If I put a positive 5 in here, I end up with 0 on the bottom. I cannot divide by 0. So, I know that I can go from 0 to 5, and then from 5 to infinity. Okay? But here's what I also need to make sure I understand. This number right here is not included. So therefore, I need to write my interval. Alright? So I'm going to start at 0. So 0 is included. And I'm going to go to 5. But I'm going to use parentheses here because 5 is not included. Then I'm going to use this little U here that says it's the union. I'm putting it together. I'm going to start back at 5, but remember 5 is not included. And I'm going to go to positive infinity. Alright? So this would be the domain of this function. If I were to graph it, well, we'll talk about that here in a moment. They're going to show us graphing here in just a moment. Alright, let's look at the third function. We have a of s is equal to the square root of 3 over 4 s squared. So what can I or can I not put in for s? This is our x. That would make this statement true. If I put a negative number in here, would it matter? No, because negative numbers squared would be positive numbers. I could multiply it, wouldn't be a big deal. Can I put 0 in there? Yeah, because if I multiply this times 0, I get 0. What about positive numbers? Can I put positive numbers in there? Yes. Alright, so in this case, the domain for this function is all real numbers. In other words, I can choose any number that I possibly want, and that would be my domain. Okay? So if you look at page 89, it does graph it for us. Alright? I'm pretty sure that they graph A, B, and C. Looking at this, graphing A, alright? If you'll go back to our domain says it has to start at -3, and it goes to infinity. Look at your x values. Look at your x values for this graph. Where does the graph start? The graph starts at -3, and it moves towards the positive side. Looking at the second one, we said that our domain has to start at 0 and go to 5, and then it stops at 5 and comes back to infinity. Look at that graph. What happens at 5? It's straight up and down. 5 is not included. So therefore, my graph is supporting what we figured out. Looking at this, for the third one, all of my x values. Guys, if I were to continue this graph up, the graph would continue to spread out, and eventually I would probably hit every single number that I could fit on a paper, on a calculator, whatever. So my domain is all real numbers. Alright, so finding the range. Remember we said range matches up with the y value? Alright, so how do we find the range of a function? So I have f of x is equal to 2 over x. So basically what I would do is I would, this is the same thing as saying y is equal to 2 over x. They start out showing you graphically. They say, okay, look at your y values, your vertical axis here. It never touches 0. It says it appears that 0 is not the domain in the domain as we thought. All right, because a denominator cannot be a 0. It also appears that the range consists of all real numbers except 0. In other words, it looks like if I were to continue this graph up, it would go as close to the y-axis as possible, but it would never touch 0. Alright, so we're going to say the range for this is every number except 0. Now, let's solve it algebraically. We want to confirm that. So what we would do is we would let y equal 0. Alright? And then we're going to solve this. I would solve it just like any time. I would multiply both sides by x. And I get 0 is equal to 2. Since we know the equation 2 is equal to 0 or 0 is equal to 2 is never true, then 2 over x equals 0 has no solution. And so y equals 0 is not in the range. But how do we know that all other real numbers are in the range? Well, I can put other real numbers in there and let y equal that and see if that would work. If you look at page 90, what they did is they said, okay, we'll just let all real numbers be k. Alright? We know 0 doesn't work, but look what happens when I let this be k. K is equal to 2 over x. Multiply both sides by x, and I get kx is equal to 2. I can put numbers in there for k and make 2. Alright? That would work. So therefore, we know the range could be negative infinity to 0, and we're not going to include 0, and from 0 to positive infinity. Alright? Alright, this next section I'm going to kind of run through. I need you to make sure you're reading it. What I'm not going to go through, we're going to talk about continuity. Guys, you'll see that there's 5 different graphs on the bottom of page 90. Alright? Continuity sounds just like continuous. If something's continuous, that means it never stops. It starts at a point and it never stops, or it may never stop in both ways. All right, so we have at the bottom of page 90, you have continuous at all x. In other words, it's going to continue on and on and on. If you will look at the second graph, you notice there is a little dot on that graph. It's almost like a break. This is what we call discontinuity. Alright? But it is what we call removable, because I can tweak my equation to change it and all will be well. Alright? Look at the next one. Once again, you have a removable discontinuity. Alright? Then you have what we call jump discontinuity. Notice what happens. There's a big break in the graph, and it jumps from one part to the next. Almost like it took a break for a moment. It said, I'm going to hide. Alright, so that is a jump discontinuity. Alright? And if you'll go to the other page, there's a little bit more of an explanation. It says it's because there's more than just a hole there. Alright? And no matter how we try to redefine that function, there's going to be that gap. Then you have infinite discontinuity. No, look at that graph. Those two graphs, those 2 points will never touch. Those 2 parts of that graph will never touch. Alright? And this is not removable. In other words, I can't fix it no matter what I do. I can't make them ever touch. Okay? So make sure you look over that next page a little bit. Alright, so let's look at page 92. Identifying points of discontinuity. Judging from the graphs, which of the following figures show functions that are discontinuous at x is equal to 2? Are any of the discontinuities removable? In other words, can I tweak it and fix that? Alright, so let's look at the first graph. figure 1.16. Alright? It wants to talk about x is equal to 2. Guys, if you look at x is equal to 2, notice it looks like that graph will never touch x is equal to 2. Alright? It is undefined at x is equal to 2. So therefore, it is not continuous. This is a discontinuity, but I cannot remove it. Remember, with this type of graph, it cannot be removed. I cannot change it. Alright? Look at figure 1.17. Look at x is equal to 2. This graph has no breaks. 2 is in the domain. So therefore it's continuous. It's continuous at x. Alright, looking at figure 1.18. Alright. Look at x is equal to 2. What do you see? There's a little bubble there. There's a little dot there. That means there's a break at x is equal to 2. So it is not continuous. It's not defined at 2. But it can be removed. It can be fixed. Alright? So therefore, this is what we call removable discontinuity. I know I'm going fast, guys. And if you have questions, all you have to do is reach out to me. I'll do my best to help you. But most of this is pretty self-explanatory. Alright. Let's talk about, and I don't know that I'm actually going to do the whole entire section because we've still got lots of stuff. But let's talk about increasing and decreasing functions. We may stop at this point. Alright, how do I know it's an increasing or decreasing function? This is one that, if you can graph it, that would be great. So let's look at this. I'm going to kind of put my book here so I can show you, I can point to what I'm talking about. So let's talk about this. How do we know it's increasing? Guys, at this point in time, if I'm following here, look at my graph. My graph is increasing. It's starting over here and it's increasing. Alright? Look at this graph right here. I'm starting here, but look, it's falling. It's decreasing. Here is a continuous graph. It stays straight. It doesn't change. Okay? Let's look at this one. This graph, it goes down. So it's decreasing from negative infinity to negative 2. Then what happens? It becomes continuous from negative 2 to 2. And then it starts to increase again. So from 2 to infinity, it is increasing. Alright? So graphing those makes it a little easier to see that they are increasing, decreasing, or being constant. Alright? But how can we identify these properties of functions algebraically? Alright? What I would like for you to do is I would like for you to kind of look at exploration 1. Okay? So it says, of the 3 tables of the numerical data below, which of these modeled by a function is an increasing, decreasing, or constant? So we can graph it, alright, but is there a way to figure out what's happening? Well, let's think about this. Let's kind of mentally think about this before we look at graphing. Okay? If I were to graph the first set of data, look at what's happening to my y's. No matter what my x is, what does my y look like? my y is constantly 12. It's always going to be 12. All right? So let's think about that in terms of what that graph would look like. Well, I'm going to put these in, and hopefully your guess is the same as what we're going to see. Alright, so I've put the points in my thing here. Let's do a quick graph. And we need to change our axes here. We'll define this one as our y. Hopefully you guessed that it was a constant. This is a continuous, a constant graph, because my y never changed. Now let's look at the second set of data. Okay? Let's look at the second set of data. Alright, so if I were to look at this, notice what's happening to my x values. I'm starting at the negative and I'm going to positive. But what's happening to my y values? I'm going from positive to negative. So thinking about that, kind of visually and mentally creating a picture, let's see what those values are going to look like on a graph. Alright, so I have plotted my point, or put my points in my thing. Let's do a data, quick graph. I need to change my axes here. Hopefully you realize that this was decreasing because my y values are going down. Look at the third one. Alright, if I look at the third one, notice my x values are starting at negative, going to positive. Alright. Then look at my y values. They're starting at negative, going to positive. Alright. So what do we think about this? Alright, could we be looking at a continuous? Or could we be looking at a increasing or a decreasing? I think you guys are smart enough that you probably know the answer to this, but let's look at it. Uh-oh. I gotta go back for just a second because something did not click. There we go. Let's change this to our x. Let's change this to our y's. And hopefully you realize that it wasn't increasing. Alright. Alright. I'm going to leave you to finish up the exploration for homework. Alright. Guys, remember, you can go on Desmos.com and use that as a graphing calculator, or if you have a graphing calculator, or if you have a phone that you can download, there are plenty of graphing calculator apps out there that are free. You just have to know how to use them. Alright, so let's look at the definition of our intervals, or our functions here. A function f is increasing if any 2 points on the interval, a positive change in x results in a positive change in y. Alright, so going back to the first one, we started in the negatives and went up to the positives. Then we went from -5 to +10. So I've got positive changes constantly happening. If it is decreasing, a positive change in the x results in a negative change in the y. So looking at the second set of data points that we did, I went from -2 to +7. That was a positive change. But I went from 3 to -12, which was a negative change. All right? And then it says function f is constant for any 2 points in the interval if you have a positive change in x results and a 0 change in your y's. All right? All right, we're going to stop here and then pick this up in the next week. Hope you guys had a great Thanksgiving, and hopefully I'll be seeing you soon.